Swayam Prabha. Digital India. Educated India.
Now, another product is wrought iron. Okay, so where cast iron, we'd already talked, cast iron has 2 to 4% carbon. Now, this is wrought iron which we are talking, which is slightly different in microstructure. Let's see what is the difference. It has less than about 1% carbon, okay, whereas in cast iron you had 2 to 4% carbon and 1 to 2% slag. Okay, that's the key thing there, key ingredient now. So, you have both carbon and 1 to 2% slag is there, mainly silicon, phosphorus, sulfur. These are the contents which are present in the slag. Now, because of this, there will be a formation of a grain structure. Okay, as we have recalled this, you might remember this image in in the nature of materials module. We had a detailed discussion on these grains. You can see grains in different directions and all that, grain boundaries, all this we discussed. And then these grain boundaries helps in preventing the crack propagation. So, they have a significant role on the mechanical properties, etc. Now, how is this made? So, it's heated and then worked. And this worked is kind of, the wrought word is coming from the word worked. So, it's similar to a strain hardened or that kind of process. So, it's bent and during the manufacturing process, it's not just casting like in case of cast iron. Here you also have cold working involved when we talk about the wrought iron. Okay. Now, main thing is it has slag also as an ingredient, and so slag, carbon and iron, these are the three main ingredients, and because of which you have a grain formation, and because of the grain formation its mechanical properties are very different as compared to cast iron and ductile iron, and it is lighter and stronger. Okay, it's lighter and stronger. So, because of this lighter and stronger, that kind of properties, it's used in many engineering applications. One of the first application is wrought iron. I mean, a noticeable application is wrought iron used in Eiffel Tower, okay, and also in Statue of Liberty. The frame inside, what you see when you see the Statue of Liberty, the green the shell is made of bronze or copper element, but the inside, the frame is made out of wrought iron, because it has high strength and it is lighter. When you talk about these large structures, the dead load or the total weight of the structure also have to be minimized. If the total weight is going to be very, very high, then what you will have a huge challenge of creating a good foundation. That also will become very big. So, there is a need for reducing the total weight of the structure. So, that is why they go for lighter material or less dense material, less dense, okay, or density is less and strength is high. So, this is just an image inside view, this one inside view of the frame inside the Statue of Liberty. These are all collected from the internet. You can see also these different aesthetically pleasing shapes for various applications in buildings, fences, etc. Wrought iron is widely used. Okay. Now, and it's less harder than the cast iron also, okay, because of the reduction in the carbon content from about 4% to about 1%, the hardness also decreases significantly. So, it's easier to So, there are advantages and disadvantages of these various properties. So, we have to see what is that you need, okay, for various engineering applications. Now, let us look at all these three material at once just to kind of summarize. So, you have cast iron on the left side, which is mainly having flaky graphites. Because of that, your brittleness of cast iron is very high. Ductile iron on the middle picture, ductile iron, it has this globular graphite. So, the brittleness decreases, ductility increases, and we call it ductile iron. And both these cast iron and ductile iron has high hardness, high strength, corrosion resistant, etc. Now, another product was wrought iron, which is having a grain structure, okay, a grain structure here, and it has less carbon than the cast iron or ductile iron, but it also has slag present in it. Okay. Now, because of this presence of slag and lower quantity of carbon, this has a strength which is higher than the cast iron, but at the same time it also relatively light because of the presence of slag in there. You remember in that blast furnace image we saw that slag actually floats above the molten iron. So, definitely slag has a density which is the density of slag is less than that of the molten iron. So, when you include some slag inside the material, definitely the density of the material is going to be slightly less, and so it is stronger because of low carbon. So, it is more widely, I mean it is widely used for engineering applications. Examples we look at Eiffel Tower and Statue of Liberty and many other typical applications in buildings. Now, let us look at steel, how steel is manufactured, and we will also talk why it corrodes. Okay. Now, steel is again similar way, you get the iron like from the iron ore to the blast furnace, and then you get the molten material, and then you, depending on the raw materials which you put, you get this particular composition of steel well controlled. And steel means there could be lot of other elements present in that for addressing various properties. Essentially, when you talk about alloys, a lot of elements come into the picture. I will show up here that details later on in the following lectures. And then what you do is you put the steel through a mill in which you get different shapes, whether it is a steel reinforcing bar like circular rod or a square shape or an I section or whatever shape you talk about, you pass it through some mechanical dies and then you get the steel. Then what you do, when you use the steel in construction, it gets exposed to moisture. That is where we are talking how it corrodes. Okay, it gets exposed to moisture and chlorides, carbon dioxide, oxygen, etc., and which leads to some of the chemical reactions. And essentially what is happening is the steel has a higher energy level than the iron ore, right. As you heat and as you pass it through the mechanical dies, both the heat energy and mechanical energy utilization is there. And so, this energy, both this heat and mechanical energy, thermal or mechanical energy, gets stored in the steel. Now, a material which has higher energy level will definitely try to react with the environment and tries to go back to its original energy level, which is that of the iron ore. So, if you look carefully in these equations here, these are the corrosion reactions. You will see that you have ferrous hydroxides and Fe2O3 forming, and then what is essentially that Fe2O3 is essentially the iron ore. Okay, the chemical structure or mineral structure is similar to that of the iron ore. So, even there is a definition that the corrosion is nothing but the extractive metallurgy in reverse direction. Okay, extractive metallurgy in reverse. So, this is corrosion is equal to extractive metallurgy in reverse. This is one of the definitions given in one of the NACE books, I remember. Okay, so essentially when during the manufacturing process of steel, the energy level of steel increases because of the heat treatment and the mechanical treatment which is given, and that energy, because of that high energy level, when it becomes in contact with the environment, it will try to go back, and now this rate of corrosion you can control by various means. Okay, so that's all advanced level courses. We will not cover those things in this class, but what you need to know is when you talk about stainless steel, this rate of corrosion is very, very small as compared to a typical other steels which are used. Now, steel manufacturing process, so just another sketch here, you can see here blast furnace, you have raw materials and then you have blast furnace, the materials are put in the blast furnace, and then either an oxygen furnace or an electric arc furnace is used depending on the energy and the resources available. Mostly now people are going for electric arc furnace, and then you convert this, the molten material is put through a mechanical shape or dies, or and it gets into these shapes, either a billet or a bloom or a slab. Okay, and then after that it is passed through some dies where we call rolling. So, you can see these are rotating wheels here, you can see here rotating wheels. Okay. There are different manufacturing processes. There are some cases where the wheels are rotating, and then there are some cases where it is extruded. So, different depending on what you are making, but for this simple understanding for this class, we can say that they are passed through some dies, metal dies, and which are harder metals. Okay, so that the die does not degrade, but rather you get a different shape. So, you can see here for one example I am showing where you can see here on the left side you have a thicker material, it is passed through a metal die, two wheels you can see, and as it comes to the other side, so this rotates like this, and then this rotates like this, and then it comes out and you get the desired shape. So, like that, depending on the shape which you want, you have these different processes involved. Okay, different shapes you can make. So, different type of steels depending mainly on the carbon content, that is how normally they are divided, okay, or classified. As you see here, if the carbon content is less than 0.15 percentage, we call it dead mild steel. From 0.15 to 0.3 percentage, we call it mild steel, and then from 0.3 to 0.8 percentage, we call it medium carbon steel, and then you have high carbon steel, okay, and then you also have hard steel. So, you can see the different percentages and how they are different. Or cast iron comes like 3 to 4 percentage, which is higher than this, but that is cast iron, and we are not mixing that into here. Here we are talking about steel, where the percentage is more or less than 1% is what we typically talk about. Okay. Now, how this carbon content varies, this carbon content influences the tensile strength and hardness of the material. So, let us look at this solid curve here, this one. So, that is a tensile ultimate strength or tensile strength of the material. You can see as the carbon content increases, initially the tensile strength increases, and then at about 1% it peaks, and then if you keep on increasing, then the strength decreases. Okay. Now, if you talk about hardness, Brinell hardness is discussed here, where how it is done is you have a spherical ball indentation, and then if you have a plate something where you kind of apply a force, and then you look at what is the indentation and diameter of that, and etc. So, I mean this is the okay. So, like this you can measure the hardness, you can read more about that in textbooks, but what you notice here is as the carbon content increases, the hardness also keep on increasing. Okay, hardness also keep on increasing. Now, what about ductility? Ductility actually decreases. Okay, as the carbon content is increasing, ductility decreases, and it after the about 0.8, it does not have much of an influence, but you can see that ductility decreases. So, there is always this danger of do not keep on increasing the carbon content, because that will definitely increase the brittleness of the material or decrease the ductility of the material. So, for engineering applications, considering the safety and all that aspects, we want the material or whatever material we use, we want them to be ductile in nature. If it is not ductile, there will be catastrophic failure, because you do not realize that it is about to fail. So, that's the main idea. So, to avoid those such catastrophic failure, or to keep the structures flexible in nature before it collapses, or it should deform significantly so that people can see that it is deforming and escape from the building or whatever facility you talk. So, you need the structures to be ductile in nature. So, we need ductile material to be used. Okay. So, ductility is very, very important aspect in addition to the strength of the materials. Now, where do we use steel in construction? One of the major application is reinforcing steel. About 30% of the steel made in this country is used as reinforcement. It's for reinforcement, okay, or these round rebars which you see, which is used in concrete construction. About 30% of all the steel which is made in the country is about rebars. Then we have structural steel, where it is, so this is an example of reinforcing steel. You can see rebars. And when we talk about structural steel, we are talking about this trusses, plates, rear bar, square shape or something, which is not circular rebars, but pipes. Structural shape means I section, angle section, channel section. So many sections are there. There will be another lecture on that coming up. And then cold formed steel, we already discussed what is cold form earlier, and studs, truss members, roofing, cladding, and of course fasteners. All these elements, they need to be connected together by using either bolts, nuts, washers, etc. There also these kind of different steel products are heavily used. And nowadays also when we talk about formworks, we have steel formworks nowadays. And this is just a quick look at different type of rebars. We will have a detailed discussion in the next lecture. Just want you to give a feeling of this, that there are different type of rebars in the market, as you can see on different pictures. Of course, there are coated rebars also. This 7, 8, 9, 10 are coated rebars. Okay, sorry, 7, 8 and 9 are coated rebars. These are coated rebars. Then this is fiber reinforced polymer rebars. So, that is just coming separate, but anyway, focus is that steel is used for making steel reinforcement. So, first 6 of them, you can see that they are all completely steel products. Okay. Now, these are the different channel or different structural steel shapes, I section, and then here also you have looks like I, and then channel, angle, and then you have sheet piling. Different shapes are there. This is just a quick summary on how different type of steel sections are, or they look like. Again, we will have a detailed lecture on this coming up. So, this is just to give you a flavor of what you can expect in the coming lectures. Now, properties of these different iron and iron products and steel, let us look at corrosion resistant. Of course, cast iron, wrought iron, etc. has higher corrosion resistance than the steel, just because of the energy consumption. I already discussed that. And then ultimate strength, of course, steel will have much higher strength as compared to other products, but let us look at this graph here. Pure iron, it is very, very less. As pure iron ultimate strength is somewhere about 60, 70, something like that, KSI. Okay, that KSI stands for kips per square inch. Okay, kips per square inch. Okay, that is KSI. Okay, it's similar to the megapascal. Okay, now cast iron is somewhat in between the wrought iron and the pure iron, and then as you go for steel, you see that the strength keep on increasing. You look at this red arrows over there, the strength keep on increasing. You have high carbon steel where strength is much higher than the mild steel. And not only strength, you also see that elastic properties here, the slope of these curves also keep changing. That means modulus of elasticity also is increasing. Okay, and so if you have a stress strain behavior graph, you can actually learn a lot about various products. And now also you see mild steel, you have a plateau region here. Okay, you have plateau region which is missing in this high carbon steel because of a lot of elements present, the alloying action. You have a gradual transition rather than a well defined yield point. Okay, so that these are all the different features of the blue arrows indicate kind of the yield strength, and you can see that there is a plateau up to mild yield, but in the high carbon alloy steel there is no plateau, yield plateau. And brittleness and ductility, as you can see here, the brittleness and ductility. So here you can see that ductility keep on decreasing. Okay, if I look at this, so ductility for the pure iron is much higher, ductility is higher, or the percent elongation is going to be higher, but as compared to the high carbon steel. So as the strength is keep on increasing, there is a general trend that ductility decreases. But nowadays we have products where within a particular range of products you can still change the chemical composition and still get that ductility even with higher strength. So that's all possible, but this is just a general discussion on how pure iron, cast iron, wrought iron, mild steel and high carbon steel behaves. Okay. So to summarize, we looked at how these four materials, cast iron, ductile iron, wrought iron and steel are produced in general, and what are the major properties of this and how the carbon content actually influences the ductility, the strength, the hardness, etc. So with that we will just close this lecture. Thank you.